lesson. And on Monday's class, we have finished the discussion on Newton's laws. And in particular, we have spent some time talking about the concept of the friction. For example, the static friction and the kinetic friction. Friction is something that would oppose the relative motion between two surfaces. So you have two objects and the surface in contact is the place where the frictional force occurs. It is the frictional force that would impede the movement of the objects when it is subjected to an external force. Say at here, you have the x-axis corresponding to the increasing external force. Y-axis corresponds to the frictional force between the two surfaces. There are two regions. In the first region, we call it static region. You cannot see the note. Okay. Now let me show it. Yeah, it's a bit tricky. Right. Right. I hope you can see it now. Although there should be, well, okay, you see the two boxes right at the right-hand side because I have to keep on checking the messages from you all the time, and apparently people are coming in, so I'm sorry that I have to keep them all the time. We have two regions. The first region is the static region, where the object is not moving. If you do not have the external force, the frictional force is simply absent. You do not expect the object to move. According to the Newton's first law, object would remain stationary when there is no net force. So if no net force, then it means the forces are canceling one another, or there is simply no force at all. Because no external force is applied, that means no frictional force. If you keep on applying a greater and greater external force, the object still does not move, which means the frictional force keeps increasing, and it is equal in size but opposite in magnitude compared with the external force. At a certain critical point, the equilibrium is broken, the object will start to move. Once it starts moving, the frictional force between the two surfaces would be a constant. So in the case of a static region, the maximum frictional force, which is this point, the maximum frictional force is proportional to the normal force acting on the object. So if you put on more weight on the object, then the reaction force acting on it increases. Then the frictional force or maximum frictional force will be increased. The proportionality constant is μs, the coefficient of static friction. And on the other hand, you would have the kinetic region, the region when the object is moving. So you have the frictional force that is a constant. And the proportionality constant now is the coefficient of kinetic friction. There is a difference between the two. Usually the coefficient of static friction is larger than the coefficient of kinetic friction. So here are some numbers. Once again, students are very keen to memorize anything. That is what I would not suggest. I would not suggest memorizing these numbers. In any case, the numbers are just for reference. They could be changed easily if you have a piece of steel that is roughened and put on another piece of a roughened steel, the coefficient of friction would be much increased. On the other hand, if you have a very smooth piece of steel put on another smooth one, then the coefficient of friction would be much reduced. So having the numbers are just for reference, and it is no particular value to memorize them. And today, we would try to finish up two topics. The first one is the circular motion, which is a special type of motion under a constant, well, under a force. I would not say a constant force because, as you will see later, the size of the force may be constant, but the magnitude is definitely not constant. It is changing from time to time. So I have to be very careful about my wordings. And the second topic that I will try to finish is the concept of energy. In particular, I would focus more discussion on the, well, force work done by varying forces, as requested by some of your classmates. So it is page 81 here. The work done by a varying force. Conceptually, it is quite straightforward. Although the operation may be something scary, you will start to see all these in the next 2 hours. Calculus, differentiation, and integration. Once again, the actual operation is not what we are interested in, but we need to know the concept. So that is the first one. The second one is the concept of the elastic potential energy. We have probably learned about gravitational potential energy and also kinetic energy. So I'm not spending too much time on those two topics. I will be talking about elastic potential energy. It is the energy stored inside an elastic object, such as a spring. When you are extending a spring, you need to apply a force. And in a certain sense, energy has to be supplied in order to change its shape. So that is what we would talk about. And finally, we would conclude with the conservation of mechanical energy. That is the idea for today's lesson. So let's come back to the lecture slide of circular motion, and that is page 65. Okay. So the idea is we try to solve some problems of uniform circular motion. Remember, now we are trying to see a circular motion of a particle-like object, going around a circular path and making a constant speed travel. Now, a lot of assumptions are here. The first one, it is a circular path, of course. And second one, it is a point object moving along a circular path, on a circular path with constant radius and constant speed. The important point really is the constant speed and a point object. If you do not have a point object, the calculations would be much more complicated, and that would be lecture notes number 2. If you do not have a constant speed, once again, calculation would be much more complicated, and once again, lecture notes number 2. So here we would be going through simple point object moving in a circular path with constant speed. And that is what comes next, the derivation of the equations. Now, at here, we try to derive the equation, a very important equation. related to the circular motion. But before we derive the equation, let us understand what is happening. Here, you have a point object, say this plug, that is moving along a circular path with, very importantly, constant speed. The speed is constant, velocity is not. It changes direction, so the velocity is changing. That is an important point. So the object moves with a constant speed along this circular path. And over a certain time delta t, it will sweep an angle theta from the center of the circular orbit. So what is the relation between this theta and various parameters here? Well, if I zoom in, you might get a little bit blocked. So it might be good actually if you can also have a slide, but let me try a bit. See it here. Yeah, it's not looking nice, but you will see what is happening here. You see the object after a time of delta t, it will sweep a distance s. Well, this s is actually the length of this circular arc, and it will sweep an angle theta that extends at the center of the circular path. So we could try to relate theta to various parameters. For example, s and r. Because if it is making a circular path, s, which is the length of this arc, it would be related to r and theta by the equation here. Of course, if it is a very large angle, the s is no longer, well, it's no longer close to the straight line. And this one is strictly applicable, but you may not have an exact geometry. In any case, here, we write it down as it is the circular path. So S over R equals to theta. The angle is in the unit of radian. And S, which is the length of the circular arc, it would be related to the time of travel delta t and the speed v, or velocity. Here is velocity, but we just take the magnitude. So that would make sense, v times delta t over r. On the other hand, we could also see that theta is related to the change of velocity as well. Now, over a time delta t, the velocity changes. Initial velocity is this one. Final velocity is this one, because the particle is moving in the anti-clockwise direction. So this is the initial velocity. This is the final velocity. Change of velocity, if you go to the deviation, it would be Vf minus Vi. So it would be, this is Vi, this is Vf. Vf vector minus Vi vector would be this one plus this one. Notice the difference. I am drawing minus Vi vector here. This vector is Vi. This is minus Vi. So Vf minus Vi. The delta V vector is pointing in this direction. This is the delta V vector. I hope you can see it. So if the theta angle is becoming very, very, very small, you will immediately see that the direction of delta V is pointing towards the center of the circular path. If theta becomes very small, the vector delta V points towards the center of the circular path. So this is why we would expect an object undergoing uniform circular motion, it would be accelerating in a direction pointing towards the center of the circular path. And what about the magnitude of the acceleration? The magnitude of the acceleration, according to definition, delta t over delta v. Well, sorry, delta v over delta t is the opposite. Okay. So delta v over delta t, according to what we have here and here, where we adjust the terms. So delta v over delta t is v squared over r. So that is why we have the equation magnitude of the acceleration is v squared over r. And the direction of the acceleration is pointing towards the center of the circular motion. So that is the idea of the what we call centripetal acceleration. It is pointing towards the center, so it accelerates towards the center. So we have this centripetal acceleration. In terms of the magnitude, it is v squared over r. In terms of the direction, it is always pointed towards the center of the circular path. So these are the important ones. In the vector form, you may express it in some other format. It is negative v squared over r times the unit vector r. Now this one, we give it a special name. We call it the unit vector. And this particular unit vector has a magnitude that is equal to 1. So 1 unit as a magnitude. And the direction of this unit vector is the same as the direction of the radius vector that points radially outward. It points from the center to the outside. So that is why the acceleration vector has a minus sign in this equation, because the acceleration, centripetal acceleration, it is pointing towards the center of the circular path. So that is how we write for the centripetal acceleration in a vector form. But if you are just using the values, then it is okay. You just use the equation at top to calculate the size, and you know that the acceleration always points towards the center of the circular path. So things are okay. And for those who are really mathematical in terms of the thinking, here we provide another mathematically elegant method to prove the equation. So idea is we can rewrite the trajectory or the location of a particle moving in a circular path by such an equation. The geometry is seen at here. Particle at a distance r from the center of the path. So we put the origin at the center. We put the origin as the center of the circular path. And the object is always at a distance r from the center. So we have the x and y axis. The angle that is swept through by the object from the x-axis is theta. At any time, the location of this object can be written as this one, r cosine theta plus r sine theta. well, I vector and j vector, of course, to represent its location in the x-axis and the y-axis. And you are having this r vector being the displacement vector. So if we have the knowledge of the calculus, which I do not assume, but let us try to do it in any case. In the concept, it is the derivative, is the differentiation of the r vector with respect to t. The operation, for those of you who have learned calculus, it is simple. For those of you who do not know calculus, it is ugly. Any case, we forget about them. Similarly, acceleration, it is the derivative of the velocity with respect to time. Again, the operations, we forget about them. But the important point here is we have, at the end, an equation that connects the acceleration vector to the displacement vector with a quantity that is called angular velocity. Angular velocity. This angular velocity is actually related to the linear velocity, as we will see later, by the equation here. V is equal to R times omega. Omega is basically how quickly the angle increases or decreases with respect to time. And V is how quickly the linear motion has taken place with respect to time. And they are related to one another by the equation V is equal to R times omega. Similarly, linear displacement, well, or the displacement along the track S is related to the angular size theta by the equation at here. So if you divide the whole equation by delta t, you could kind of imagine obtaining the equation here. So from that, we could change omega into V over R. And R here, the vector is basically the whole vector R with the direction in the radial direction and size equal to the original size. So it is equal to the magnitude R times the unit vector. And so you retrieve the original equation back. Once again, this is for those with mathematical training in the calculus, and just for demonstration. For other students, the equation we have seen here, which is derived from the concept here, should be sufficient. Okay, having talked about all these centripetal acceleration AC, we have the understanding that an object, when it is undergoing a circular motion, uniform circular motion, it must be receiving an acceleration that points towards the center. Where comes the force? According to the Newton's second law, if an object is accelerating, there must be a corresponding force that helps the acceleration. So when an object is making a circular motion, a uniform circular motion, there must be a centripetal force that helps the object to move in the circular track. This is the scenario which I guess many of the boys would have done that, maybe the girls as well. You have a plug attached to a string. Well, simple experiment. I would not encourage you to do at home, but you can always do that. You will tie something, say your mobile phone, to a string, and then try to swing it, well, at your own loss. You try to swing it, and so it can make a circular path. There would be tension in the string, because if you want the object to move in a circular path, what it takes is you need to have a centripetal force that keeps the object in circular orbit. If the tension is lost, for example, the string suddenly breaks, oh, your mobile phone is gone, then the object would no longer perform a circular orbit. But at the point when it breaks, the object, according to the Newton's first law, would carry on its linear motion with constant velocity. So it moves along the tangent of the circular path at the point where it breaks free from the tension of the string. So when the object is making a circular path, it is under the influence of a centripetal force. Once the centripetal force is absent, the object would carry on its linear motion along a straight line. That is the idea of a circular motion. So here we try to take a look at an example. Sorry, I have to maximize a bit and then try to see if it works. You have this pendulum, which is a mass attached to a string, and it is swirling in a circular track in the horizontal direction. So we are trying to find a equation that expresses the velocity of the object when it is undergoing this circular motion. How do we do that? For this problem, we could always start by drawing the free body diagram. What are the forces acting on this object? Well, when it is making a circular path, it is attached to a string, and there must be weight acting on the mass. So you could draw the force diagram, tension and the weight. There is an imbalance of forces. In the vertical direction, component of the tension in the vertical direction balance the weight. Otherwise, the object will start to accelerate downward. On the other hand, now you have this object moving in a circular path. The center of the circular path, which is a horizontal path, it is, say, in here, in this scenario, on the right-hand side of the mass. So it points towards the center of the circular orbit. So the tension component, horizontal tension component, provides the centripetal force. You could now relate the tension and weight to the circular motion, because T sine theta, it is equal to m times v squared over r. Well, m times a is equal to the net force. So you have the equation for connecting the tension, theta, velocity to r. And what about the angle theta? Tangent theta, it is equal to, well, at here, you divide the two equations, 1 and 2. So tangent theta is 2, well, 2 divided by 1. So it becomes tangent theta, and the right-hand side is v squared over rg. So you have the equation for the velocity in terms of r and theta. R is the radius of the circular path. Now be careful here. R is the radius of the horizontal circular path. It is this one. It is not the length of the string. The length of the string is L, and it is related to R by L sine theta. It is the triangle at here. So L and R related by the sine theta. So that is why we have the equation shown in this way. something you have to be very careful about. The circular path has a radius r, and it is different from the length of the string. Then let's take a look at some other examples. Say at here, we try to consider, say, a car taking a turn around a corner. So for the car to take the corner, it has to. Why do we need to change what? Can you be more specific? Well, you are not really provided with R. You are provided with the length of the L. And actually, R changes. L does not change. So that is why we are expressing in terms of L rather than R. So here we have another example, car taking the corner. So in order to take the corner, it is basically undergoing circular motion. Only part of it, only part of the circular motion, because once it takes the corner, it may go along a straight line. But along this circular track, it is taking a corner, undergoing circular motion. So in order to undergo circular motion, there must be a centripetal force. Direction of force points towards the center of the circular track. So if it is a circular track, say something like this, I try to draw a track. If it is a circular track that goes like this, the center of the circular track may be somewhere here. So at this location, for example, when the car comes to this location, it would have the centripetal force pointing towards the direction of the center of the circular track. Right. Where comes the force? Where comes the centripetal force? It would be coming from the friction between the road surface and the wheels. You do not have a string to pull the car. It must be coming from the frictional force. And that explains why on a raining day, it is very dangerous to make a turn, because the road surface is slippery. It does not provide sufficient frictional force for the turn to take place successfully. Anyway, here we have the frictional force, which is, well, if the wheel is in contact with the road surface and it is not slipping, basically, well, that is something we would discuss later, actually. Basically, at the point of contact, the relative velocity between the road surface and the wheel is 0. Now, that is very strange to the students at the first sight, but it is related to the nature of the circular motion. A car that is moving forward, you would expect the wheel to be rolling on the road surface. It does not slide on the road surface. If it slides, you will see there is a very thick layer of the rubber on the road surface. That does not happen. If it happens, it is very dangerous. When the car is moving on the road, it is actually rolling on the road surface. At the point of contact between the road surface and the wheel, in the whole, the wheel is moving forward, but the surface of the wheel at this point is actually going backward. So by some calculation later, we will see that at this point, the velocity is exactly 0. The velocity at this point would be 2 times the speed of the car. It changes according to location, but at the point of contact, the velocity would be exactly 0. So that is why we have here coefficient of static friction that is appearing instead of a kinetic friction, because you are not sliding the wheel on the road surface. But in any case, you have the frictional force. And here you have a car that is okay, trying to make a turn. So you have the maximum frictional force that is equal to mu s times n, and that is equal to mv squared over r. The centripetal force is mv squared over r. The force comes from the frictional force. But actually, I'm sorry, I'm kind of mixing up. Here, the frictional force is actually along the radial direction. It is not along the movement direction. So it actually has to be present in order to provide the frictional force. In any case, this wheel is not sliding into or out of the radial direction. So in the radial direction, the car is not moving. It is not changing the radius of the circular track. So it is a static scenario. So now, along the y-axis, which is the vertical direction, N is the reaction force, and it is equal to the weight. So you could put it into the equation and obtain the corresponding equation for the maximum velocity. So this one would tell you, in order to take the corner safely without sliding sideways, without sliding out of the path, then the maximum velocity you could have is 13.4 meters per second. A quick calculation, it is around 50 or 60 kilometers per hour, not very fast. If you want to do it faster, a suggestion would be, according to the next example, having a tilting on the road surface. This tilting would allow part of the normal force acting on the car to be used as the centripetal force. So this would allow us to increase the speed when the car is taking the corner. I'm not going into this particular example. Here in this example, we assume that the normal force provides all the centripetal force. But of course, in a real life scenario, you could have both the normal force components, you could have the NX, as well as the frictional force on the wheel to provide the centripetal force. But here, we try to make the things a little bit more simple. And we just consider the component of the normal force. We just use the normal force component for taking the corner. So that is the idea. Right. So far, we have been considering only a motion, in most of the time, a horizontal circular motion. Of course, circular motion could take place in the vertical direction as well. Just like if you still have not done that, you could swing your mobile phone by attaching it to a string, either as a cowboy, swinging it in a horizontal orbit, or as it is in a vertical orbit, you swing it in the vertical plane. You could do that once again, but not at my loss. You might lose your phone, but that is something you could visualize. In any case, here we try to consider what happens when you are having a vertical circular motion with constant speed. Say this is a Ferris wheel that is present in many of the playgrounds. In order to perform a uniform circular motion, we would expect that the centripetal force, which points towards the center of the circular orbit, to be constant. The centripetal force pointing towards the circular orbit has to be constant. But where comes this centripetal force? That is the tricky point. As we will see, when the boy is riding on the Ferris wheel, sometimes he is at the top, sometimes he is at the bottom. For example, when the boy is at the bottom of the circular orbit, what are the forces acting on him? It would be the normal force at the bottom, well, acting on the boy from the seat. And there would be gravitational force, well, the weight acting on the boy as well. It is the difference between the two which points upward that contributes to the centripetal force. So that is why you have in here n bottom minus mg equals to mv squared over r. Are they the same? N bottom and mg, are they the same? They cannot be the same. Because if they are the same, that means this would become 0. It would not be a circular motion. The n bottom would be larger than the weight of the boy in order to successfully perform a circular orbit. So that is why after some calculations, you will see that at the bottom of the ride, the boy will feel a little bit heavier because we sense our weight according to the normal force acting on us. So at the bottom of the ride, the normal force acting on the boy would be slightly larger than 1 mg. What about at the top of the ride? At the top of the ride, we still have this force diagram, weight and n top. But this time, the weight would win over n top because the centripetal force is pointing towards the center of the orbit. And it is underneath the boy. So here you will see mg minus n top, which points upward. It is equal to mv squared over r. What happens? After some calculation, n top is slightly smaller than 1 mg. So you will start wondering what controls the coefficient in front, what controls 1.09 or what controls 0.908, why not 0.7, 0.6? It depends on the terms at here. As you will see, it depends on v squared and r. Okay, let us have some fun. We try to change not the radius of the circular orbit, but the velocity or the speed of the circular track, of the circular motion. If the speed keeps on increasing, that means v gets larger and larger. This one would get smaller and smaller. At a certain point, what would happen? At a certain point, if v squared is larger than rg, then we would expect n top to be 0. That is dangerous because the boy would feel weightlessness, just like he is free falling. So it would be very dangerous if the velocity or the speed of the circular motion is high. And one of the important things the boy should do actually is to put on a seatbelt, trying to catch him downward if the speed is too high, or to catch the rail in front of him. Otherwise, he would really be lifted up from the circular motion. So that is something you have to be careful about when considering the circular motion in the vertical direction, because the size of although the centripetal force size does not change, what makes up the centripetal force would be changing. For example, the normal force acting on the body. So that is the idea of the circular motion. And just to get you some examples or exercise to work on, here I have put up some simple questions for you to try concerning the frictional force as well as the centripetal force. So there are two of them, I think. Let's take a look at the question first. So the first one is concerned with a ball being swung in a vertical circle, and we are trying to determine the tension in the string. So that is related to circular motion. And question number 2 is asking you about the frictional force acting on the car, or the total force acting on the car. So I would be leaving behind the short quiz to you. During the break time, we would have a break around 10 minutes. And after the 10 minutes, we would stop the question, and I will briefly explain the answers before we continue with the second part of the lesson. Okay, so please try to make use of the time to take a break or try to finish the 2 questions.
I'm sorry, sir. I got a question about example 6.3.
Yes. Okay. Yeah.
In the first line, it said, first line of the calculation is that the maximum friction is equal to mu times n.
Yeah.
And I wonder why it is also equal to the m times the v squared over r.
Well, if you take a look at the camera that I'm actually showing the paper, I will try to show you the deviation over there. So let me try to turn it on. Okay. So why we have the frictional force? It is because if we take a look from the top, it is a car trying to make a circular path. Okay. So there is a centripetal force. And where comes this centripetal force? If we take a look from the back of the car, it would be due to the frictional force. It would be due to the frictional force acting on the wheels. If there is no frictional force, the car would be sliding outward. You would probably imagine that even with the daily life experience. You try to take a corner, but does not succeed. And then you would just go along a straight line. So you leave the circular orbit. So in order to make a successful turn, you need to have the centripetal force. And this centripetal force comes from the frictional force. This frictional force, because the car, it is not sliding sideways. It is not sliding into or out of the circular track, it is the same as the frictional force. This centripetal force is equal to the frictional force until the maximum static friction is reached. When the maximum static friction is reached, if you try to increase the speed further in order to provide the centripetal force, it cannot be provided through friction and it would leave the circular track. So that is why the maximum centripetal force available, the maximum F2, it is equal to mv max square over r, and that would be equal to the maximum static friction, mu s times n.
Actually, I understand the concept, but I'm not sure why the maximum friction is equal to the m times the v square over r, because v square over r should be the centripetal acceleration.
Yeah.
But
So,
why m times that centripetal acceleration is the maximum friction?
you are having an acceleration, or you need to provide a centripetal force. And you need to have the centripetal force in order to have the centripetal acceleration. Does it make sense to you?
Yes.
Mm-hmm. So
yes,
if you have the centripetal acceleration, which is v squared over r, where does the force come from? It comes from the friction. Would it be, did I answer your question, actually?
I think yes.
Okay.
Thank you.
Okay. Is it suitable for n bottom smaller than the net force? And it can still keep the circular motion. The idea is not how large is n bottom or n top. The idea is what is the net force in order to keep uniform circular motion. It is the net force. The net force is the difference between various force components. So whether it is large or small, at the end, it is decided by what is the resultant net force required. Answer that one. Final answer, how many significant figure or well, I don't know if you have been taught about significant figures in your high school. These questions keep on coming up. It is reasonable to give a significant figure values that is accurately describing the physical problem and yet make sense. If you are saying that I am 2 meters tall, well, I'm not saying that you are wrong, but I might just be 1.51 centimeters, which I'm cheating quite a bit. So having one significant figure is definitely not something we want. A reasonable number would be something like 3 to 5 significant figures. Anything more than 6 would be very tricky or very dangerous. In many calculations, I have seen students copying all the numbers in the calculator, which has around 11 digits. Think about it. If you are trying to tell that your height is 1.65823456 meters tall. It really depends on what time of the day you are. In the morning, you have the hair that has not been combed, so it is a little bit higher. And after gelling your hair, it gets a little bit shorter. And even if you move up or down the stairs, they may jump. So having very detailed numbers, unless you are supported, it is not reasonable. So I would say 3 to 5 is usually a good number. And in the intermediate calculations, please keep reasonable accuracy, because error can propagate from the first part of the question to the last part. So if your final answer has to be 4 significant figures accurate, then your intermediate steps has to get at least 5 significant figures, one more figure than the final answer. Okay. If a tire is frictionless, or I should say, if the friction between the road surface and the car is 0, then you have to provide some other means to turn a corner. For example, in the universe, how does the spaceship turn the corners? Well, they rely on the gravitational force. Or if they want to change the course of the motion, they have to turn on their jet engine. So that is some net force provided. In the case of a car turning corners, typically they rely on friction, of course. 9.8 or 9.81, I would accept both, but if possible, starting from this day onward, please use 9.81. Let's be a little bit more scientific. 10 would be a little bit too rough. Well, yeah, from today onwards, let's say 9.81. I'm not saying you are right or wrong, but yeah, let's try to be, in your examination, actually, you would also use 9.81. We would not say that it is wrong. We will not say that it's wrong. Okay, seems there are lots of questions. I don't know which one to answer now because I actually have to start the lesson. I will leave it until the end of the class, and you please stay behind, and I'll try to address them one by one. Okay, now I will leave the quiz on until the end of the class, so you will still have some time to handle it. At the moment, let us focus on the lesson. Let me see if I'm sharing. Okay, I will share the slides again. We have someone trying to take my screen. Someone wants to do the teaching for me. Okay, no. Okay, we come back to the lesson. Okay. Right. Okay. Now, we would here jump to the next topic, and that is concerned with the energy and conservation of energy. We are still in the topic of the mechanics. So we would be focusing on the mechanical energy. Not many types of energy you have learned in the mechanical case apart from kinetic energy and gravitational potential energy. But all the discussions about energy will start from work done. And that is the fundamental concept related to energy. So we will start from the discussion of the work done before we uh, quickly look at the equations, just the equations of the kinetic and gravitational potential energy. And we will put more time on the elastic potential energy. So here we take a look at the idea of the work done. By the definition, when you have a force that is exerted on a system and try to move it over a certain displacement, then there would be a work done to the system. The idea is quite easy to understand. For example, when you have, say, this force that is exerted on the object during the course, assuming, say, there is no other forces acting on it, you have the displacement delta r. And in between the force vector and the displacement vector, there is an angle, theta. So the work done is given as what we call a dot product between the force vector and the displacement vector. The operation of the dot product is mathematically equivalent to the magnitude, the product of the magnitude for the two vectors and cosine of the angle in between them. So from this equation, we could understand that if the force is parallel to the displacement vector, then we would expect the maximum size of the work done. So the work done is the energy that is provided by the external force to the object due to the displacement. So when you have the force that is applied parallel to the displacement, then the work done associated to it would be the largest. On the other hand, in some situations which you could figure it out from the last set of lecture notes, if the force is perpendicular to the displacement all the time, then there would be no work done because the angle between the force and the displacement is 90 degrees. So cosine 90 degrees is equal to 0. So there will be no work done in that situation. So that is the scenario if the force is perpendicular to the displacement, then there is no work done. And of course, things are simple if you have the force that is constant and it is always along the same direction. But there are scenarios in which the force and the angle, they are changing. So you would have a situation in which the work done is due to a varying force. Let us just try to look at the situation when only the force is varying. For example, you have this force Fx along the x direction that is changing during the displacement of the object. So the force and the force is changing, and then it keeps on as it keeps on moving along the x-axis. So how do we calculate the work done in this case? The concept is like this. The concept, at least, is like this. At a certain point, say from xi to xf, the displacement of the object may be delta x. Let us assume naively that the force in between xi and xf, it is a constant. If the force is a constant, then we would be happy because we could apply the equation that we have seen previously to our calculation. Fx times delta x. But that is only applicable in between xi and xf. After this region, so from xf to another location, the force has changed. And then you have to calculate the work done by using another force. So in a certain sense, if you look at my writing, try to put it here. If you look at my writing, it would be, so the Fx, say, xi, which correspond to the force at the location xi, times x f minus xi plus fxf. That is the second location, the force at the second location, and it will be x, say f2 minus xf, because it has moved from xf to xf2, and so on. So the force has changed. We just calculate the work done by adding up the work done in different regions. In a certain sense, you could treat it as a rectangle, or if you like, the area under this part of the graph. So this is the area between the force graph and xi and xf. The next one, this one, is the area of the next rectangle. The area of the next rectangle under the graph. So at the end, how do we calculate the work done by a varying force? We just add up all the rectangles. Conceptually, that is the idea. We just add up all the rectangles under the graph. Or to be more precise, we are calculating the area under the graph. Area under the graph of the curve. So how do we do that? Mathematically, we could write the equation in this way. We are summing all these f times delta x from the very first point of the displacement to the very last point of the displacement. So we add up all these rectangles. And according to calculus integration, if the delta x is very small, then what happens is we could rewrite the equation like this. This would be, according to the integration, rewritten in such a form. So you could see the similarity between the two equations. Fx here, delta x is replaced by dx. You could, in a sense, consider it as changing from a finite width delta x into an infinitely small width dx. And this is the sum of individual terms. You are having all these rectangles. Here, you are putting a sign of the integration that corresponds to the summing up of infinitely many terms. As long as they are from xi to xf. That is the idea of the integration. You are, instead of doing a what we call sum of the finite terms, so we have a finite number of terms at here. We have a finite number of terms here. And then change it into a mathematical operation, which we are actually summing up infinite number of terms, but we are not actually using our fingers or calculators to do that. We use integration to do that. So conceptually, it is the idea. And you could see that we are basically finding just the area under this graph. So that is how we calculate the work done when we have our varying force. Later, we'll see this will become useful. Of course, you do not understand how to operate the calculus or integration for now. That is okay. But conceptually, conceptually, it will be the area under the graph. Okay. So let us come to something that you are more familiar with. Well, is it the operation just like the trapezoidal rule? Trapezoidal rule is exactly what I have mentioned. It is for discrete mathematics. It is for summing up finite number of terms. But if you have infinite number of terms, you would start running into trouble, especially when you have a variable force. Okay. So yes, the idea is similar. So kinetic energy, which is something you are familiar with, you know the calculations much more than me, so I will not go into the details. Equations, the definition of the terms, something you know. So here is just a quick deviation of the kinetic energy. So why there is a term of the kinetic energy? We consider it as the result of conversion of energies. Work done is energy. You are imposing energy to the system. So what is used to characterize the energy? We could characterize the energy by considering the motion of the object. According to what we have seen, the work done by the external force it is equal to the sum, well, it's equal to the integration of the F, well, net force. Here we are talking about the net force times dx, and then we do the integration. This net force is, according to Newton's second law, equals to m times a for this particle. So with some mathematical tricks, we could rewrite a as dv over dt, and replacing the terms m times dv, well, m times dv times dx over dt. dx over dt is the velocity. So we have this equation. Mathematically, in terms of calculus, we could obtain the answer for this calculation by some operations. So this would be the result of the operation. As we will see it here, the two terms are very similar. They have the format 1/2 mv squared. Only difference is that the first term has the final velocity in the v. Second term has the initial velocity in the v. So we could say a particle has a special energy property that is related to the motion. And this special energy related to motion is what we call the kinetic energy. And the kinetic energy at any part of the motion is determined by 1/2 mv squared. So that is why we have the change of the kinetic energy due to what? Work done. That is how we understand the deviation at here. And of course, the work and kinetic energy theorem, if you look at it in greater details, it is kind of a special case of the conservation of kinetic energy. You are just converting between the external work done and the change in the kinetic energy. When you have the external work done, of course, you expect a change in the kinetic energy. When you have other energy terms that comes in, we would consider them in greater details. But if there is only interconversion between the two, then this would be the work kinetic energy theorem. So it sounds a big name, but it is just a special form of the conservation of the mechanical energy, if you like. So at here, we have so what numbers? Session number? Okay, sorry. It is yeah. Okay, sorry. Now we have this next example, which is also the work kinetic energy theorem example, just the interconversion between the work and the kinetic energy change. So I would not once again go into the details because that is quite straightforward in terms of the application of the kinetic energy. And we also should have learned about the potential energy. A potential energy is related to the change of the configuration of the system. So, for example, in the case of the gravitational potential energy, you are talking about the change of the height of the object. And that due to the change of the height of the object, you are storing some potential energy in the object, or releasing some of the potential energy in the object, such that when you return it from the return it to the original position, the energy could be restored. So this equations tells you how the gravitational potential energy is derived. But once again, we would not go into the details. The idea is we have extracted an equation such that there is a property of the system called a gravitational potential energy. This gravitational potential energy is determined by the height of the object. We did not actually mention what is the measurement of the height. It can be from the table, it can be from the ground, it can be from the center of the earth, it can be anywhere. You need to define it. So saying the absolute value of the gravitational potential energy is kind of meaningless because you need to define what is the starting point. So we are usually talking about the change of the gravitational potential energy. It is the change that is more important. But to start with, we can define a term, gravitational potential energy, that is related to the height of the object. And we could put it into our calculations later. Okay, this would be something that many of the students may have not encountered before. So the idea is, apart from the gravitational force, which is kind of a conservative force, you could retrieve the energy when you return the object to the original height. There is another scenario in which you could store the energy or store the work done as a potential energy. And this would be the case when you are scratching a spring. The idea is like this. When you have a spring, say the one in the diagram or the one that I'm drawing on the paper, it really depends on how much you are extending the spring from the equilibrium position. So x0 is the equilibrium position where the spring does not provide any force to the object. It does not provide any force to the object. If you extend the spring by pulling the object, say up to this point, xf, there is of course a corresponding displacement, delta x. This displacement is at the expense of a force created in the spring. The force from the spring, as from your experience, would be pointing in the direction opposite to the extension. So that Fs is the force from the spring, as you will see in the diagram here. This Fs is the force from the spring that occurs when you are extending the spring from the equilibrium position up to x. If the displacement is along the positive x direction, the force, as you will see, points in the negative x direction. So that is why we have the equation here. Spring force equals to minus kx. X is the extension from equilibrium point, and k is what we call the spring constant. It is a linear relation. You double the extension from the equilibrium point, you double the force. We are always talking about the extension from the equilibrium point. That is a very important concept, actually. Of course, if you, instead of pulling the spring, you push the spring, it would actually be the same equation, because when you push the spring would try to provide a resisting force, hoping to put the block back to the original position. So if your displacement in the negative x, the force is along the positive x direction. So once again, the negative sign is applicable. So this equation is valid no matter x is positive or negative. It changes automatically the direction of the force by changing its sign. So associated with the spring force, there would be a corresponding spring energy. Now, here the diagram may not be very easy to understand if you combine it with the graph. Here, actually, the graph is talking about the compression of the spring. So it is actually the compression of the spring. So I may just try to put it as compressed. And here, if the thing is considered as compression, it may be easier to figure out. So here you have a compression of the spring. But let's say the compression direction is taken as positive x. When you compress the spring, of course, you need to provide a force. Otherwise, it is not successful. So this is the applied force. This is the external force. What happens when you compress the spring? The spring reacts by providing an opposite force. So this is the scenario. When you push the spring, it compresses. And when you apply the force and push the spring, there is work done. What is the size of work done? According to our definition of work done, W is equal to F times delta X. So it is equal to the applied force times delta X. Applied force is equal, well, if you are not pushing it very quickly or too slowly, well, you push it very slowly, then the applied force should be equal to the external force. You are not accelerating it, you're just storing energy to it. So the two forces would be just equal to one another. And otherwise, you would introduce kinetic energy and so on. So we just consider the energy associated with the spring. So the applied force would be equal to the spring force. But remember, what is the spring force? F is equal to minus kx. So applied force is actually equal to kx. So that is why you have kx, that is the force, applied force, times dx. You are having a varying force because as soon as you move from equilibrium position, the force is present, but it keeps on changing. So kx times dx. And you are moving from the initial point to the final point. Situation actually could be considered using a graph. If you look at the graph, look at the video camera, this would be graph. So this is the applied force. This is x. Hope I can. Okay, here is applied force against x. This is what we expect. Kx equals to F applied. And what is Kx dx? It is the area under the graph. So you can see area under a triangle. It is 1/2 kx squared. Not very special. Here the height is kx f, for example, and if this is xf, that would be the elastic potential energy stored at the position Except if your starting point is xi, then it would already have some elastic potential energy stored to it. So it is just like the energy is dependent on the starting point as well as the final point. If your spring starts from 0, then the total elastic potential energy would be from the 0 point up to the final point, except. But if you are starting from the middle, xi, you are just considering the energy change in between, in this region. So that is something you have to be careful about. When you consider the elastic potential energy, it is the final value, elastic potential energy minus the initial value. And you have to be careful about what is the starting point and what is the final point. In general, the elastic potential energy at a location x is measured from the equilibrium position. The elastic potential energy is equal to 1/2 kx squared. So that is the idea. Okay. And this is the calculation for the elastic potential energy. Conservation of energy is something you have seen before. The initial total energy must be equal to the final total energy. And there may be other mechanisms for the energy loss. For example, due to friction. Work done sometimes has to be provided in order to overcome energy loss due to friction. So here you have the equation that connects the initial kinetic energy, final initial mechanical energy, final mechanical energy, work done, and the work against friction. Work against friction causes loss to the initial energy. Work done provides energy to the initial system. So the final mechanical energy is related to all these terms. Okay. Conceptually, it is not very difficult. You could actually make sense of all these terms, I think, by looking at the equations. So it would be good for us to take a look at some examples to consolidate the learning. Say at here, let us start with a simple example. You have a ball that is dropped from height h above the ground, and you are asked to determine the speed of the ball when it is at height y above the ground. By conservation of energy, we consider the energy terms are associated with the two different positions. What are the energies at this point? It would be just the gravitational potential energy. At this point, it would be gravitational potential energy, kinetic energy. Well, here you have kinetic energy equals to 0 because it is dropped from rest. So considering no work done against friction, this would be what you need. Kf plus Uf equals to Ki plus Ui. Some of the terms are 0, and the initial gravitational potential energy is mgh, final mgy. So you have the equation for final velocity. Energy is not a vector. So all the energy terms are scalar. All the energy are scalar. The force are vector. But once you have the dot product, once you calculate it into energy, it is not a vector, it would be a scalar. Okay. So the energy would increase or decrease, but it is no longer a vector property. And if you are asked to determine the speed of the ball at y, if the sphere is initially having a velocity vi, you just need to change, in this case, the initial kinetic energy. So calculations are exactly the same equations, but the form may be slightly more complicated. So not much of a difficulty, I believe, for most of the students. Next example, this is a block that is pulled along a rough surface. So it might be a little bit more challenging. You have a block 6 kg that is pulled to the right by a constant force, 12 Newton. Find the speed of the block after it moved 3 meters. If there is a surface that has a coefficient of kinetic friction 0.15. So first, we draw the force diagrams. We understand what are the forces. Normal force, weight, pulling force 12 Newton, frictional force. Because the object is moving, well, we actually should decide whether it is moving or not. The frictional force, maximum frictional force, well, it is not provided, but let us just take a look. 0.15 times the normal force, it would be 0.882. So there is a surplus for the force in the x direction. There is a surplus for the force in the x direction. It did not really say whether what is the static friction force, but we kind of assume that it is moving at here. Strictly speaking, we should provide you with the static frictional coefficient to determine whether it could start moving in the first place, but that would be just another layer of complication. Here, we assume it is moving. And so, what are the forces? That is all here. The size has been determined. And then the energy. We have the block initially having a velocity vi and final velocity vf. So we write down the conservation of energy, final kinetic energy equals to initial one plus the work done by the force F minus work done against friction. It is the frictional force times the distance, F times d. And the work done is F times d, F times delta x, actually. So I don't know why it has to put the d and delta x to make the things complicated, but they are actually the same value. So we could see how it is calculated. Not much of a difficulty in this part. And then try to add another layer of a complication. Now, the force is not applied horizontally, but it is applied at an angle shown in the diagram. Only, well, it is not that simple in this case because first, you have the force that is separated into two components. You have the horizontal force that is together with the frictional force causing the horizontal motion. And then the vertical component is partly balanced, is partly contributing to overcome the weight of the object. So the force acting on the block would be slightly complicated. In the case of the work done by the external force, it is equal to F times delta X times cosine theta. That is okay. The force in the y direction, it would be N plus F sine theta minus mg. So the normal force is mg minus F sine theta. Now, think about the conservation of energy. Final kinetic energy is equal to initial one, which is starting from rest, so 0. Frictional work done, it is mu k times n times d. And then the work done by force F is Fd cosine theta. So we have a equation. Now it is depending on theta, which makes the things quite complicated. The complication can be solved if we know a bit of a differentiation. If you are not yet ready to accept differentiation, that is okay, but I try to explain the concept here. We are having a curve. So this is the equation of the kinetic energy, final kinetic energy versus theta. You can see that in the equation shown at here, Kf equals to something, 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 theta, sine theta, plus something, something, cosine theta. You can treat it as a kinetic energy, final kinetic energy versus theta. So you could draw a graph. Well, I'm not asking you to actually draw out the exact graph, but think about it. It may be a graph like this. Now, in the question, you are asked to find out the largest possible speed, which in a sense is just the largest possible velocity of the block. No, yeah, largest possible speed, of course, is largest possible velocity. Largest possible speed, largest speed would be equivalent to highest Kf, kinetic energy in the final stage. So what is the point where you have the largest kinetic energy? This point in the graph. What is special about this point? In the graph, you could see that at the maximum point, the slope of the graph is equal to 0. The slope is equal to 0. So,
1, 2, 3, 4.
So at here, we have to apply the differentiation. By considering the slope at various points, dk f over d theta, which requires some mathematical operation, and considering the location where the slope is equal to 0, we could determine the point with maximum kinetic energy, maximum final kinetic energy. Of course, you would argue another possible scenario, and that is the kinetic energy, final kinetic energy versus theta, actually is a minimum point. But we have other ways to determine whether it's maximum or minimum point. Here, we just go through the concept. So that is why we have the differentiation at here. After some operation, we determine the corresponding value of theta that gives the maximum kinetic energy or maximum speed of the block. Okay. So that is the idea. Right. Well, I cannot really control what you are trying to do when you are, which helps you to focus on the lesson maybe, that's okay, as long as you mute. So I'm not too much concerned about it. And many of the examples in the lecture notes, they would be also related to the conservation of energy. I would leave them to you to take a look. And hopefully, by now, you have finished the quiz. There are still one or two who have not submitted the answer. Well, I think I have to stop at it here because I would like to explain the answer actually. Okay. Right. So let's come back to the question. And maybe this one first. Now, this car is moving from rest, and it starts to roll on a horizontal roll surface. What is the total force acting on the car? Well, you have to consider that in order for the car to start moving, actually, you cannot have a smooth surface. The road surface must be somehow rough for the car to move. And you cannot have the road surface that is smooth that allows the cars to roll forward. So let me see. Okay. Yeah. It's hard to. Okay, I should be now showing the question. I hope. Okay, so the car is moving forward. Well, the car starts to move forward. And in order to start the car moving, there must be some frictional force. And also the car is being supported. Therefore, there must be normal force. At the end, the two forces would add up and it would be the resultant force. You may be wondering why it has to be pointing forward for the frictional force, but not pointing backward. It is the idea of the wheel rolling on a roll surface. So at the point where the wheel is in contact with the roll surface, I explained it before, it is actually trying to slip backward. So the relative motion is that frictional force would try to prevent the wheel surface from keep on moving. And so the frictional force has to be pointing forward. And this would actually make sense because without the forward component, the car actually cannot move forward. You need to accelerate the car. So it is somehow, strangely, provided by the frictional force in order to help it to move forward. Okay. So that is the first question. And the next question is, let me see. Now this one, you have a ball attached to a string and it is swung in a circle of radius 0.5 meter. And the speed at the top is 6 meters per second. What is the tension in the string? If I try to draw it in the diagram, I just need to consider the forces. So there would be centripetal force. This centripetal force has to be provided by the weight as well as the tension in the string. So you just set the two together. Yeah, I think classmate has provided you with the equation. If you have the centripetal force larger than the, well, if you have the centripetal force larger than the weight, then, well, I should write it as a whole, Fc equals to mg plus t. If the centripetal force is not very large, then T would become negative. What does the T negative means? It means nothing. It means nonsense. T has to be positive in order to pull the string, in order to pull the ball backward. If the centripetal force is not large, that means the velocity is not high. You would expect the ball actually not able to maneuver the highest point in the circle. It will just drop and hit your head, basically. If your revolving is not fast enough, there is no tension in the string. If the revolving is not fast enough, centripetal force is not high. And the centripetal force comes from the weight plus tension. That means the tension is not large and even becomes negative. Physically, that means the string is relaxed and it is not making a successful circle. That is the idea. So this is the concept, and I will try to check the answers later and tell you the results on the blackboard. So later this week, you would be receiving the second assignment through the blackboard. There will be 6 or 7 short questions and should be easy to finish. And you will be having 1 week to complete all the questions. Okay, so in next week, we would be jumping to the next topic, and that is the linear collision, linear momentum and collision. And we would finish them within next week. And hopefully we have some time for some actual tutorial questions.